Okay, let's look at 8.4, property number 3. Right? So let P, which is just a collection of set A sub alpha, be a partition of A. A's are just a non-empty set. Right? Then we define relation on A as we say X is related to Y if there exists a set in the partition such that it includes X and Y. So if there's a set that contains both, then we say these two guys are related, right? The claim is this relation, it turns out to be an equivalence relation, right? So we need to check all three conditions, right? So let's look at the reflexivity, right? So we're going to look at, so we have to show that for all element in A is related to itself. So I'm going to say choose any element, say A, in A. Right, so this is just a given. Right, we need to show that this A is related to itself. Right, so 2. Right, so since A is an element of A, there must be a set in the partition that contains A. Right, so there exists some alpha in the index set such that A is contained in A sub alpha, right? This comes from the definition of partition. I listed the 3 conditions to become a partition. This comes from the third one because the union of all these set, a subgroup, has to add up to the entire A, which means that the one of these guys have to contain every single element. For every element, one of these guys have to contain that element. So this comes from, I'll just put definition of partition 3, right, which indicate that one right there. All right, if that's the case, so A is in this subgroup, also A is in this subgroup, so by definition of this relation, right, we know that therefore A, because A is in this subgroup, then of course A is in the subgroup. Kind of silly to say that, but so we have that. All right, so this comes from line number 2. Right, so this verifies the reflexivity of this relation. All right, let's check the symmetry. Right, so we have to show that say 1. So we assume that say A is related to B by this relation R. So this is just a given. All right, then we want to show that the B is related back to A. All right, so let's do that. So 2. All right, so by definition of this relation, there must be some alpha in the index set such that the both A and B is contained in set A sub alpha, right? So this is just a definition of R, the relation R. It's right here, right? So 3, right? If A and B are in the subgroup, then of course B is related to A by this relation, right? So that comes from 2, right? Then that will establish the symmetry, because if A is related to B, B is related back to A. So we have that. All right, so third condition is a transitivity. So let's check that. One, right? We assume that say A is related to B. At the same time, B is related to C by this relation, right? Then we need to conclude that the A is related to C by this relation. So this is given, right? And line number 2, right? By the definition, if A is related to B, that means that there must be some alpha in the index set such that A and B both belongs to A sub alpha, right? So that's just the definition of R. So I'm using 1. All right, and 3, also, since B is related to C, so there must be some index beta such that the B and the C are both in A sub beta. So that comes from 1, right? But you can see that A sub alpha and A sub beta shares element B, which means that because this is a partition, they're either disjoint, pairwise disjoint, or if they're not disjoint, which means that they must be identical. So so it's 4. We know that A alpha is actually same as A sub beta. Using number 2 from the definition of partition. Alright, then since A sub alpha and A sub beta are the same, so we know that the A and C is in A sub alpha or beta. So it's going to be 5. Therefore, A and C are both in A sub alpha. Right, so that comes from so we know that 2, 3, 4 combined. So line 2, line 3, and line 4 combined. Right? That will show that, oh, actually, I have to go one more step, so maybe I should do that. So 6. Right? So therefore, we know that A is related to C. Right? So we have that. So that comes from 5. All right, so that will establish the transitivity of this relation. All right, so therefore, from 1 to, we check all 3 conditions. So hence, this relation R is definitely an equivalence relation on A. Okay, that's it. I hope that this was clear.